everyone. So we're moving on to the next topic, which is Intro to Electrostatics. Now, you should have learned through those worksheets some of the basic stuff. A lot of stuff is coming from chemistry. The things like the fact that electrons and protons are carrying the charge. For atoms, there's neutrons that don't have any charge. Um, that the charge on an electron and proton are the same, that electrons are the only things that move. All these things are important, but I wanted to talk about one of the other aspects to electrostatics. Before we continue, I just want to think about this question. So, if you've never done this before, or if you have a rubber balloon on hand, I recommend trying this. If you take a balloon, rub it on your head, or rub it on a piece of wool, you'll find that it will actually attract and stick to a wall. Now the wall is neutral. And now the question is, will the ball stay? Will the balloon stay there forever? Why or why not? So I want you to think about that real quick. And as we probably know, eventually, if you watch the balloon long enough, it will eventually fall. So it won't stay there forever. Now the reason why that would happen has to do with the fact that if it's not sticking to the wall anymore, that means it must have lost its charge. So there's two different ways that it lost its charge. Through contact with the wall, a little bit of the electrons will actually start jumping off onto the wall. But another thing, and actually one of the more important things that's taken the charge away, is actually the water molecules in the air. The water molecules will actually interact and start taking some of those electrons off the balloon. You can actually test this at home, uh, where you take a balloon, you rub it on your head, put it on a wall. Do that in a very humid day, and then do that on a very dry day. Typically, what you can try doing is doing it when your house is fairly warm, and then open up a window, get the room really cold, and then try it again. And you'll see that when it's really cold, really dry, the balloon will actually stay there much longer than on a very humid day. And that's because of the lack of water molecules in the air when it's dry to take away those charges. All right. Now, so this is actually just a visualization of what's going on. So here we have an electroscope that has a bunch of charges. There's excess electrons. The water molecules will come in. This is actually because a lot of the water molecules tend to be polarized, so they actually can take away some of that. Some molecules are actually already ionized, and that's what ends up happening. So this is just a little visualization of that. So one of the things that we wanted to talk about is we can actually see charge using something called an electroscope. Now, an electroscope, as the name implies, is a device used to see charge. It can come in a variety of different ways, but the most common one that you'll see is one of these. So typically, it's a metal ball at the very top. It's connected down with a pipe, and then at the end of the pipe are two leaves. Usually, the leaves are made of gold or some other type of conductive metal, maybe even aluminum if it's a very cheap electroscope. And then it's housed within a glass canister. And the idea is that if you bring a charged object close to the ball, it will cause the leaves to separate. When the leaves actually move, either towards or away from themselves, that's a sign that we have an electroscope, that we have a charged object near the electroscope. All right, so here's an electroscope. I have a little simulator for so that you can see it. Here you see that we have a movable negative rod filled with excess negative charges. I have a finger here too that I could fool around with. And then here's my electroscope. Like I said, it has a conductive metal top, and then at the end are conductive metal leaves. Right now, it is a neutral electroscope due to the fact that there's equal amounts of positive and negative charges. Remember, neutral doesn't mean no charge, it means balanced charges. So, what we can see is that as I bring this negative rod over, you'll start to notice that these leaves start to separate. The leaves separate because every time I move this closer, these negative charges repel the negative charges down to the leaves. So I'm moving the electrons down. Now, and then what's left are the positive charges. Remember, positive charges never move. It's only the electrons that move. You can think about it like when doing some of the practice questions, the multiple choice questions. You could think to yourself like, okay, this end's going to be positive because positive gets attracted to the negative. But just remember that any question that says something about what charges move, it will never ever be the positive charges because it's only electrons that move. But yeah, so this is ends up what's happening. The negative charges end up moving down to the leaves, and because of the excess negative charges at the leaves, they push against each other and separate. So this is how we can tell that this charge, this rod, is charged. It doesn't just work with negative charges; it also works with positive charges. But unlike before, where instead of repelling the negative charges to the leaves, now we still have the leaves separating, but now it's caused by the fact that the electrons are actually leaving the leaves, going to the top to be closer to the positive rod, leaving behind only positive charges. So the leaves separate a lot because of that. And then, so this electroscope, like I said, can tell whether something's positive or negative, but when it's in a neutral state, there is no way to actually discern what type of charge. Because regardless of whether I used a positive rod or a negative rod, the leaves are still separated because of the fact that of what charges are there. The only way we'd be able to tell what specific type of charge we have is if we charge this with a known charge. So if I actually set it up like this, right now there's more positive charges than negative. So this is a positive electroscope. Bringing the negative rod over actually causes the leaves to come together. But if I move a positive rod, it causes them to separate more. And again, that's because positives repel, positive electroscope, positive rod, opposites attract, positive electroscope, negative rod. So this, like I said, this is the way that we actually can tell that something is charged, is by looking at the electroscope and seeing what happens to the leaves. All right, so now we have a few different ways that we can actually charge an object. So we know how we can see charge through the electroscope, but now how do we actually get an object charged? There's a few different ways of doing this. First way is through friction. So friction is just taking two objects and rubbing them together and getting something. Basically, what ends up happening when you rub them is that you're literally taking electrons off of one object and then putting it onto another. So it's not just any two objects. Usually, it's very specific objects. Um, but this is the main way of getting charged. In fact, is through friction. Um, the charge will always end up being equal and opposite. That's because every time one object removes an electron off of the other object, it gains it. So one becomes positive and one becomes equally negative. We actually have a defined definition of what objects actually result in what type of charges. This was actually defined by Ben Franklin, oddly enough. He did a lot of tests with rubbing objects, and he found that when he rubbed silk on a glass rod, it ended up the rod ended up with a different charge than when he rubbed a fur cloth on a rubber rod. So what he defined was the rubber as being negative and the glass as being positive. Um, and that's actually where our definitions, our terms of positive and negative actually come from this definition of glass rods becoming positive and rubber rods becoming negative. Now, another way that we can get charge is through something called conduction. This is usually means that we already have an object that's charged, and we bring it and touch it to another object. Here, they're going to exchange their charge to balance out. And the charges will always balance to be equal charge as related to, equal objects at least. And this is how we can kind of get a new charge on something. So conduction is through contact. You can see it in the word contact. Now, the third and final one is called induction. Now, the main thing you need to know about induction is that the objects do not touch. so they never actually touch. There's a whole excess set of what you have to do for this. In fact, I kind of showed it before. Basically, the idea is you have to include this third thing called ground. So you bring the charge object close to the object that you want. Uh, Charge separation occurs, so the electrons go to one side, positives are left on the other. We connect that neutral object to ground, and ground is defined as an infinite well, an infinite source of charges, something that can either give or take charges without really feeling any effects. For small objects, we can be considered ground, but for most objects, it's the actual physical ground. The Earth is our biggest source of ground. Then the electrons will actually flow onto the neutral object or off of it through the ground connection. Then you remove the two objects, and now what you end up having is the object having the opposite charge of the rod. So like I said, I actually did this before. I'll try to show it real quick in a second. All right, so back to the simulator. Once again, I have my neutral charge. So this finger is actually acting as the ground. And now when I move the electrons, without the ground, the electrons go to the leaves because they want to get as far away from this rod as they can. So when I connect this to ground, instead of going to the leaves, they decide that they're going to go through the ground to get, again, as far away from this rod as possible. And I get further and further away. Now, if I remove the rod first, all it does is allow for the electrons to decide to come back, and I end up still with the neutral electroscope. But instead, if I remove the ground first, then when I remove the rod, uh, those electrons can't come back, so now I end up with a positive electroscope. Again, I can do induction with the positive rod. Here I add electrons from the finger because again, electrons want to be here. I remove the finger, remove the rod, and now I have excess electrons stuck on the electroscope. I started with a positive rod, I now have a negative electroscope. So the main thing to take away from induction is that the charged object and the electroscope never touch, and we end up getting opposite charges. That's the main thing to take away from this. All right, so here's your first question. Pause the video, work itself. We'll go over in a second. All right, so right off the bat, you don't even have to read the question. We can immediately get rid of two of these choices. I can get rid of choice B and choice D because, as we know, protons never move. So, regardless of what the question says, the fact that B and D mentions protons moving means I have to disregard them. So now I'm left with A and C. If you're going to guess, you're now at a 50-50 shot. Now, going back to the question, it says that a plastic rod is rubbed with wool. The wood acquires a positive charge. Now, if the wool acquires a positive charge, that means it has more protons than there are electrons. Since it couldn't have gained protons, that means it must have lost electrons in order to get that positive charge. So now I need to read choices A and see which one is mentioning electrons leaving the wool. And the only one that does that is choice A. Electrons are transferred from the wool to the rod. So the rod becomes negative, the wool becomes positive because of the electrons going to the rod. All right, here's the next question. Pause video, work itself. We'll go over in a second. All right, once again, I can get rid of two choices because they don't really make sense. They say that a positive rod is held near the knob of a neutral electroscope. Because they haven't touched and it's only held near the knob, that means the electroscope should still be neutral, equal amounts of positive and negative charges. So choices 1 and 2 have to be thrown out because those two electroscopes are charged. One is positively charged and two is negatively charged. So now we're down to 3 and 4. Both of these have equal positive and negative charges at the top and leaves. Now I have to think about what would happen. Since I'm bringing a positive rod near the electroscope, positive rods attract negative electrons. So we should be looking for the scope where electrons are as close to possible to the positive rod. And the only one that does that is choice 4. The one where negatives are close to the rod, positives are far away from it. Right? And that's pretty much it. Um, One of the things to take away from this, like I said, is the idea of charge separation, how the electroscopes work, because that actually is an extremely important part. It's a very common concept question to be able to see, what we use to see charges, how we can charge objects, conduction, induction. They have similar names, so you want to remember the difference: induction, no contact; conduction, contact. Now, as you also know, one of the things that really comes up is that as charges build and build and build onto an object, eventually those excess charges don't want to be on that object. They're always trying to find a way off of a charged object. So if you start building up too much charge, eventually what's going to end up happening is those charges will end up jumping off of you and resulting in a static shock in order to kind of neutralize you. This is actually what happens a lot of times when you rub uh, let's say your feet on like a carpet or something, or maybe you're getting in and out of a car and you touch a metal door or something metal, something conductive. All of a sudden you get that shock that hurts off your fingers wherever you were going to touch. And that's because you had built up all this excess charge that wanted to get off of you. So when your hand got close to that conductive material, it all jumped off and resulted in this static shock. This is actually one of the reasons why it is super dangerous to go back into your car while you're pumping gas. You may not know this, but most pumps used to have a trigger on them in order to actually keep it so that you can just lock it in place and then go back in your car, hang out there while the pump is going. A lot of places have now outlawed it because it turns out if you go into if you start trying to fill up your car with gas, if you lock it and decide to go into your car and you hang out, sit in your car, if you come out and you actually don't discharge yourself before touching the gas pump, there's a chance that you may statically shock the gas, ignite it, and result in a fire causing at the gas pump. If you don't believe me, you can search it on YouTube and look at gas pump static charge. There's plenty of videos like that. It's actually another reason why you might see some signs saying don't use your phone at a gas pump, because it's a similar thing. Sometimes the phone might give a static shock and that could ignite the gas. So be careful for those who have licenses already and for those who are about to get licenses, because it can get dangerous sometimes. All right. If you have any other questions, feel free to let me know. Contact me if you want. Uh, if Yeah, you can send me a message on Remind. Otherwise, I'll see you later. Good luck and have a great day.